let's get going. Now, we're going to look at magnetic field lines today. So, I'm going to flip this bad boy across. And let's start. So these little map compasses, they themselves are little bits of magnetized metal, and one side is painted red and it points north. So it's called the north-seeking end. Alright? It is actually a north magnetic pole, and the black side is a south magnetic pole. Okay? And what happens when you place them in an external magnetic field? They are going to align themselves. So what we say is, well, I'm just going to take him over a bit because I'm going to have this separate over here. They're going to align themselves. Now I've got to make sure I get this right. The field lines, like so. Okay, now I've just drawn a line there to represent a magnetic field. Same as electric fields, the density of the lines is an indication of the strength of the field. The only way we can really test the strength of the field is with a test charge. We will learn about charges moving in magnetic fields will also experience forces. So we'll get to that later on. So in electric fields, you put a little test charge and go, all right, that's the direction that the positive test charge would experience a force. That's the direction that it would travel. With magnetic field lines, we could put a little compass map and go, well, that's the direction. Oh, here we go. That's the direction that the compass map would align itself. So, again, this red side is the north magnetic, and I have a fear of these spikes. Nasty looking things. And if you allow it to balance, it's going to align it. Oh, look, what's it doing? Huh. I don't know, not quite sure what it's doing. Why are you wobbling like that? It shouldn't wobble. It should align itself north. Are we agreeing that north's that way?
No.
Where's north? North's that way?
So the table legs? The table legs there?
No. There isn't any. There shouldn't be any magnetic field. Oh, maybe. Oh, Jesus.
They're ferromagnetic. Remember the badge stuff?
I thought the red end was going to point north. Any cadets or orienteers or?
Yeah, that's when you got there.
Suggesting north is that way. All right, I got my colours the wrong way around. So hold on to your hats. If I was to place my little compass map down here, it's going to align itself such that the north-seeking end aligns itself with the field. Okay? Again, what's happening is one side is a north pole and it's going to be magnetically attracted to the south pole. So again, if you just put a compass map, you can consider the different forces on either side of your compass. There's going to be an attraction of the north to the south side and an attraction of the south to the north side. If you were to put it halfway, then there's going to be a turning effect. As the attraction occurs, all of those compass maps are going to align themselves. Okay, so you can sort of go, well, we could track the direction of the fields by getting these compass maps and moving them around a magnet, and you would see this kind of shape, that they travel away from the north end and then point towards the south. For field strength, it's a little bit trickier because we don't really have a concept of force with our compass maps. For field strength, we could get our little iron filings, as I've shown you, and you see that the strength is very strong at the poles. Again, doesn't really show it very well. So let's just quickly get to the page where we are drawing field lines, which would be, here we go. Oh, look at that. Now, page 18, I believe. Drawing magnetic field lines. There are a couple of rules that you need to be hitting. And we will write them down here. So, they always point north to south. They are vectors, and as such they can combine, they can cancel. You can work together, you'll get a stronger field. If you've got two opposing fields, they would cancel out such that the net magnetic field strength is 0. As I've said before, the density is a representation of the field strength. As such, they will never cross. Same as electric fields. Your field lines will never cross. They can get very, very close together. You can have a very, very dense field, but they cannot cross because that implies infinite field strength. As well, it is a conservative field. And how do we show that in our electric fields? How do we... Symmetric. And then same as the electric fields, let's leave the surface at 90 degrees. Okay? So, I've stolen a nice diagram. It's showing the field lines inside the magnet. Well, we don't really draw the field lines inside the magnet, like we don't draw the gravitational field lines inside the Earth. We just want to draw the external magnetic field. We can't really look at what's happening inside the magnet. We can't put a test charge or a test blah, blah, blah. So let's go outside. So straight away, let's just draw in. Field lines always travel from north to south. So you can put that one in. Now, you can draw it around like so. Ooh, was that? No, I've a bit of a bump there. Try and draw it as symmetric as possible. Follow the rules. From north to south. Whatever you draw above, you draw below. Now that, again, the bottom right is a little bit too far out compared to above. Oops, so I'm going to redraw it as best I can. You can, if you run out of paper or room from north, oops, I've stuffed up over here, that should be to south. Remember, these loops will always be complete, so they can travel out. But remember, the loop that I drew at the top, that would go around and then return back to here. So each outgoing line needs to have its own incoming line, which, again, that follows the symmetry, that follows the conservative field. If I just drew one line here and I didn't draw that one out there, that line doesn't have his partner, okay? You can, if you want, draw off to the side, but generally we draw them at the edges, okay? Now, so we'll just leave that for now. So how many lines have I got there? Four lines, 5, 6, 7, 8, 9, 10. There's 10. Again, what you need to show is the further away you get, the field strength does decrease. And in fact, the strongest region is going to be right here at the edges. Okay? So if you look at the diagram over here, you've got the strongest field is going to be at the South Pole and at the North Pole. Anywhere else, as you get further away from the magnet, the field strength would decrease. Okay? Now, let's go down. Let's look at some combinations. In this case, when you have a south and a north pole brought near to each other, this is where we would take the idea that they are vectors and they're going to combine. So basically, we're going to draw lots of field lines north to south, like so. Not the best diagram, but you can also draw your outside from north to south. You could draw one going off here, one going down there. Remember, he would also complete the loop. Now, it is open to interpretation. You can draw okay. And what I will encourage you guys to do, oh no, let's not do that. Let's just do a surface to surface. All right. Now, is that right? Are we happy with that? If I said they were equal strength magnets, what are we missing? All right, so again, still slice it down the middle. Vertical and horizontal should be symmetric. So I would include a field line north to south. I don't have my keyboard on me, person, at the moment, but I would encourage you to Google image search magnetic field lines of dipole magnets. And you'll get various arrangements. So I will quickly show you. I stole some images from the Google the other year. So, and I'll place these. My right eyeball's starting to go on me. I'll place these on the OneNote, but you can get two magnets in different arrangements. You could have north to north pole, in which case this looks very similar to your identical charges, drawing the field lines. They're vectors, so they will start to cancel. All right, so in this middle bit region, you've got from north and from north. Well, you've got two vectors equal strength in opposing directions. They will cancel out. So you'd have to draw a bit of a void. And then obviously this is what we drew. We drew the region in between the north and south. But then you can get these weird ones where you can take your magnets and have them parallel. Okay? Now, we want to have a little bit of a rule here that if the field lines combine and connect, then that's going to symbolize an attractive force. Okay? So this bit here is attraction, whereas the void is repulsion. So you can sort of make these little rules and go, well, what would occur? Well, if the field lines don't connect, they're going to repel. Basically, you do not ever see this one and this one with gravitation. Gravity is only ever attractive. So if I said draw the gravitational field lines of you and the Earth, your field lines of your gravitational fields would actually be connecting up. You know, that's you and that's the Earth. Or this was one object with equal mass gravitational attraction to the other. So that's where it breaks down. Gravity is only an attractive force, whereas magnetism and electrical fields, you can get repulsion. Okay? All right. Let's get back to the Earth is a magnet. Is that? Hang on. Wait a second. Have I missed anything on this page? No, I haven't. The Earth is a magnet. Dot, dot, dot. Sort of. Okay? Now, have I written some stuff at the bottom? Yes, okay. Before we draw the magnetic field of the Earth, it is not because of ferromagnetic materials. It is not because we have large lumps of iron. The reason being is that the majority of the Earth is very, very hot. And it's hot enough that it is above the Curie temperature. So there would be no ferromagnetic effects. But for the purposes of drawing the field lines, we could pretend that there is a giant bar magnet through the axis of the Earth. And that way it helps you figure out where the field lines are going, the directions that they are traveling. Okay? The current idea is that the very slowly moving plumes of mantle and magnet that are moving, and the friction cause produces ions, and you've got it moving very, very slowly, but it's that slowly moving charge. There's a lot of it because the Earth is big. That's what produces the magnetic field. Okay? And for some strange reason, every couple of 100,000 years, the magnetic poles actually shift. They discovered this. This was really cool. They found magnetized pockets of basalt. So when volcanic rock is made, and it's really, really hot, and when it solidifies, it actually, if it's got iron in it, it will align itself in the current external magnetic field. So this is really cool. At the bottom of the sea, there's regions called sea floor spreading. Have you heard of sea floor spreading, where you get plates going out either way like a conveyor belt? What they found is where they knew that the sea floor spreading region, they found that it was aligned certain ways, but then as you got further from that region, the magnetization actually flipped. And so if you knew the rate at which the seafloor was being produced, you could basically measure the distance from it, and you could find that the volcanic rock was magnetized one direction and then the next. And it's every 100,000 years or so. As it says, over 1,000 to 5,000 year period, as it's flipping, you would get all of these different magnetic poles appearing, popping out all over the place. That would be very, very bad. And during this period, we would be bombarded with nasty charged particles from space, which would cook us. Compasses wouldn't work. Very, very scary stuff. Let's get back to some more soothing stuff. I would like you to pretend that inside the Earth, if you have the ability to do so, draw in a massive bar magnet like so. Okay? But don't draw its polarity yet, because I'm going to draw my blue field lines. They travel out. Like so. I'm going to draw a nice conservative field, so I'm going to draw a few off into nothingness and a few like that, and then maybe just two more like that. Boom, done. Brilliant. So, just draw that for now. Don't worry about the arrows. Ignore the arrows for now. I've already kind of spoiled the surprise. Okay. So your ancient explorers, your explorers from a few hundred years ago, when they figured out that there was a magnetic field that always seemed to point north, and then when they painted their north-seeking end, right, paint the tip red, and the side that's your north-seeking, it was actually the north geographic seeking. So up here we have the North Geographic Pole, NGP. And then down here, we have the South Geographic Pole. That makes sense. Somebody said that up is north, down is south. Then somebody else said, let's paint the red end of a magnet. Turns out, remember our north-seeking pole itself is a north pole of a magnet. So it's actually attracted to the south magnetic. So 300 years ago, when they're trying to figure out boats and shipping and navigation, they had it a bit wrong. It's actually the north geographic is the south magnetic, and the south geographic is the north magnetic, which then makes sense that our field lines are traveling from north magnetic, from and to south.
Is that why the
And
Earth
south.
bulges at the equator?
No. The Earth bulges at its equator due to the centripetal force required at the equator, and the inertia of the mass sees it wanting to bulge out. Now, so that if you're ever asked to draw the Earth's magnetic field, again, just pretensies that it's a bar magnet, but realize it's not ferromagnetic. It's more so swirling ions in the magma. Okay? I want you to try your darndest to draw in the equator, which is the belt of the Earth. EQW, that'll do. Let's finish it off. ATOR. I would like you to consider, Brendan, close the laptop, please. Robert, close it, please. Thank you. You're good. So is he. You're good. I'd like you to consider 4 different regions on the Earth. A couple of them are quite absolute. At the equator. All right. If you are standing at the equator, I'm going to draw you standing at the equator. Your field lines are going to be travelling north. Okay? And I'd like you to just make a note that there is no vertical component. Okay? It points directly north. So again, north, south, east, west. I don't know if he's spat that down. I just decided to change the orientation of my letters. So again, if you sketch the field lines, you can see, all right, here, perfect, boom. There is no vertical component. Those lines are just travelling horizontal to the surface, and they're pointing north. Okay? Now, let's consider a person standing at the North Pole. North geographic pole. Here's the person. Your field line is pointing straight downwards. Okay? It's all vertical. Pointing downwards. Happy, happy? Cool. The other place is going to be at the South Pole. At South Geographic Pole, where down is up and up is down, and obviously which direction's the field going now? Straight upwards. And the last place that I would like you to consider is here in Perth, Western Australia. What's the direction of the field there? Now, here's my person standing in Perth. It's coming out of the Earth, all right? Magnetic field lines, they can travel through matter, all right? So can electric fields. I can put a magnet under the table and make bits of iron move around on the top of the table. Here's what it's going to look like, all right? It's going to be doing that. Now, you've now got north, south, east, and west, but now there's an angle to the vertical. So we need to now split our magnetic field into a vertical component and a north component. Okay? And currently, because remember, it's not constant, it's, the magma in the mantle is sloshing around inside the Earth. It does vary, but, at the past couple of 100 years, this angle is 66.4 degrees in Perth. So it's pointing north, then inclined at 66 degrees upwards to the vertical. Okay? Currently, we're going to say that the strength of the field is 5.86 times 10 to the 5, negative 5, sorry, Tesla. Okay? We will go north, 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 north. Now, you are not expected to memorize this, so if you were ever asked a question in a WACE exam, it would give you both the strength and the direction or the angle above. Okay? Now, there is one other unit, just to note. 1 Gauss is 10 to the negative 4 Tesla. So you could also write your B strength as 0.586 Gauss. Now, it's got some strange unit, CGS, but we're only ever going to use Tesla. That's our SI unit. Okay, and we can find there are equations that relate magnetic field strength with forces on charged particles. So it does have units of kilograms, meters, seconds, and coulombs. Okay, but more on that later. Now, here's the deal. This orientation was quite useful. If we're looking at this bloke in Perth, he's looking north, so we're looking east to west. Okay, and if we are looking east to west, we can see both components. See it side on, I can see the north component dashed line, and I can see the vertical component dashed line. But because we're in 3 dimensions, I want you to be able to change your orientation, change your view. I want you to be able to draw this as if you were looking down on him, as if you were north pointing south, beneath him, looking at his feet, behind him, facing the same direction. So what we're going to do, and I apologise if you run out of room, find a bit of spare paper in that booklet somewhere. Somebody find something. Front page? That could. Huh? Back page. All right, go to the back page. This is going to become very useful. So, back page, I would like you to draw a circle with a dot in it. That's going to represent a direction that is out of page. And a circle with a cross is going to represent a direction of into the page. The easiest way to remember this is an arrow. Oh, that looked pretty good there. Yeah, that'll do. So think of an arrow. If the arrow is coming towards you, then you're going to see the point of the arrow, okay, coming out of the page. If the arrow is coming out of the page towards you, you see the point. If the arrow is going into the page, then you're looking at the back end of the arrow, you would see the quill or the feather or a dart. You know, when you're throwing a dart at a dartboard, if the dart is travelling away from you, you see the back end of the dart, you would see a cross. This is a very important convention to represent direction of either magnetic field or force or current. We're going to be looking at 3 different vectors, and they're all going to be acting in their own plane, up, down, left, right, forwards, backwards. So one of them, whatever orientation you're looking at, one of them is going to be into or out of. One will be left, right, up, down, and one would be left and right, and the other would be up and down. So, let's consider back at good old Perth. I would like to have a top-down approach. Let's look at this person, and let's treat him like the original GTA and GTA 2, where it was a top-down platform game. So we're now looking at this guy's head. There's his shoulders and his feet. He's pointing north, and obviously east and west. This is a bad example because now we could draw in the north component of the magnetic field, but we wouldn't be able to see the vertical component. So we would have to represent the upwards component as a dot. It turns out we started with the best orientation. The best orientation is that one there, a side-on view. That's the best because we can see both components on a page. But that's what it would look like if that were the case. Now, let's look at this bloke. straight on. So now I'm north looking south. Okay? We still have, which way is the beach? If I'm north looking south, the beach is to my right and the inland is to my left. Now we can draw the vertical component, but I can't see the north component. Brendan? So the north component would now be drawn as a dot. Now let's go and stand behind this bloke. So let's just draw the back of his head. That's his pockets. That's his hair. Okay. Now he's looking north and so are we. So now, which way is the beach? The beach is to his left if he's looking north on the coastline. Now, same deal. We can see the vertical component, but now north is going into the page. And so we would draw it as a cross. Okay? So if you just want to quickly look top down. This one is looking south. This one is looking north. This will become more and more apparent as to why this is an important thing. Okay? That's about as much as I want to get through. The declination and the... Okay, so let's just talk... The inclination, that's your 66.4 degrees. That's the angle that it makes with the ground. And then your declination is true north. True north is going to... True magnetic north, I should say, is going to be the region on the Earth where there is no horizontal component. The lines are going straight up. Okay? And if you take a slice from the center of the Earth to the geographic to the magnetic, there's going to be a tiny little split. Currently, does anyone know what it is? It's like 1.5. Yeah, about 1.5?
Degrees?
Yeah.
27 mils.
27 millimeters of what?
A milliradian.
A milliradian. Oh, jeez. What's that? Two
64.
pi r pi. Okay, so it's about.
6400 things. It's 27 of those.
Okay, so here's the thing. So even though it's out by 1.5 degrees, the early explorers, it was still useful. When you are near the equator, there isn't often a difference between the magnetic north and the geographic north. It's pointing the same direction. And if you look at where the early English explorers were, you're all around the equator. If you want to get to the Far East and find the trade routes to buy spices and stuff, you're all near the equator. Asia, India, the Americas, you're all sort of near the equator. So this issue, it wasn't really a large deal. Obviously, if you're trying... the next thing. The magnets align themselves. So this magnet here, right? He wants to align himself completely with the Earth's magnetic field. But because he's stuck on a pin and horizontal, he can only align himself with the horizontal component. Let's go back to what that might look like in Perth. So he can only align himself with that. Okay? So really what he wants to do is he wants to go north and 66.4 degrees vertical. That's how he would like to act. If we could place him on a string with no external forces, he would go like that. Now, if I took this compass to the South Pole, right, there is no vertical component. And, I'm sure you've all thought about this. If you took a magnet to the North Pole, is it going to just sort of spin around like this? When you're at the North Pole, is it just going to spin around like some weird glitch in a computer game? Well, no, because remember, what would he like to do? He would like to align himself like that. Well, your early astronomers, your early explorers and navigators, they held theirs out horizontal and balanced in oil or suspended it on a pin. They needed to be in a region where most of the magnetic field was horizontal. We'll have a look at that. That's mostly this region here. All right, so compasses in oil or suspended compasses, they will work if there's a horizontal component. The further you get towards the pole, they're not going to work anymore. But again, there's nothing really worth looking at down in Antarctica. There's nothing worth exploring up in the Arctic. There's nothing good there. There's no spice. There's no seeds or nuts or saffron or silk or cotton or threads or frankincense and myrrh. There's nothing good there. It's just snow. Panda, the polar bears. Yes?
So at the equator, would the angle of inclination be 90 or 0? Like
0.
0?
It would just be north.
Yeah.
North at 0 degrees above.
I was trying to...
Now here's the next thing. One last, I'm just trying to stretch this out because I don't want to go to the next page. That's for tomorrow's lesson. One last thing. Please make a note. In southern hemisphere, your B vert is above horizontal, and in northern, your B vert points downwards. Okay? Just be aware of that. If we went to the same latitude, we're below the equator at a certain degree latitude south. If we went to the same latitude north, maybe in China somewhere, you could draw the same diagram, but your B field, go away. Your B, tap anywhere in the screen. I just tapped the screen. Why did that come up? Oh, because it thinks I want to type. If you were in the northern hemisphere, the same distance above the equator as we are below, we would be drawing the, what's that called, a reflection? Translation? Reflection. Downwards, okay? But, WACE, WA, curriculum, most of the students are in Perth. We're going to look at questions that might involve these numbers here. But again, it's not always the same. As you travel towards the equator, kids that might be up in the top end of WA, their inclination is going to be a lot more shallower to the horizontal. Yes, Robert? Yeah, I guess so. Are we? How many more time? How much time have we got left?
Alright.
So you don't actually want to go to the toilet. Are you going to come back?
Yeah.
We got 5 minutes left, don't we? 10. Oh. Did I tell you the Mr. Ray story time?
No.
Did I tell you about the?
You want to tell us more about your crazy.
Oh, so I told you about the unlimited printing.
Yeah.
Okay.
You can tell us about exactly crazy.
Oh no, well that's just a life lesson that I learned that some people are crazier than others. That's just. Let me.